Excellent. Thank you for the introduction, Ian. And thanks for the opportunity to present and for the award. I'm feel very honored to have received it, and I'm just excited for the opportunity to talk about all the fun things I got to work on and how the CLS played a really significant role in that. So currently at MIT working with Mircha with on metal organic frameworks. So it's a totally different material system, but still thinking about very deeply about electronic conductivity and electronic structure of these materials as well. And so I just wanted to begin my presentation with some acknowledgements. So I'd like to acknowledge my advisor, whose support was really pivotal and critical over the last few years as I worked on this stuff. As well as the Banerjee Research Group, and this photo is a little dated, but it's the group as I remember it for the majority of my time at Texas A&M University, and I had the wonderful opportunity to work with a lot of great collaborators spanning the U.S. and internationally, and so I'd like to acknowledge all of them, but in particular a few of the collaborators whose work I'm going to be touching on today. Also got to work with a lot of great undergraduate researchers, and I wanted to also thank some of the great, really great, and I'm missing a few here, but great beamline scientists that put up with all of our late night phone calls when there was something wrong with the end station, and for helping us to collect all this great data. And then of course I wanted to specifically thank a few of my colleagues who helped me stay up through some late nights at the beam time. So my work really focuses on metastable materials and how we can sort of use synthetic approaches to tunnel through synthetic phase space to access some of these things to tune the properties of these materials for a variety of applications, including some of the things that I've worked on in neuromorphic computing and intercalation batteries and photocatalysis. But to keep things kind of focused today, I'm going to be talking about energy storage and how we use some of these metastable materials to really improve energy storage materials at the atomistic and at the mesoscales. And so when thinking about a material for a specific application, really there's a lot of different considerations that we have to put into this, right? All the way from the crystal structure of the material all the way through the device and how that's assembled. And so really the things that we have to consider span decades of length scales, but also decades of time scales in terms of the processes that are happening from fundamental diffusion through the lattice, polaronic hopping, so electronic diffusion, as well as sort of how how lithium and different ions move through materials and how those waves propagate through the material over time. And so the systems that I've primarily worked on here is vanadium oxide. And so why vanadium oxide is a question that we get asked a lot. And really it's because it's a great model cathode material. It's not the most outstanding, on its face material out there. It's the thermodynamic sink of the V2O5 system, and so this is kind of the crystal structure. And you can see why, early on in the days of lithium-ion batteries, this was sort of, identified as a potentially promising material. It's got a lot of ample room for diffusion of ions. The crystal structure is relatively open. It has a lot of different, in terms of just the crystal structure and the composition, desirable properties, including a lot of multiple accessible redox states, vanadium 5 to vanadium 4 to vanadium 3 potentially. And the problem is really, and this was realized early on, is that there's really sluggish diffusion kinetics. The material has a really poor electrical conductivity. And then as we lithiate this material, there's also a series of irreversible structural transitions that really prevent us from getting at accessing a lot of the potential energy storage that it has as we pump lithium into this. And so really what we've been interested for a number of years, going back to before I joined the group and now even continuing on, is what are the fundamental origins of this, the poor performance of this material, and how do we get at improving its performance at an atomistic level and at the mesoscale in terms of the actual cell design and everything. And so really what it comes down to is that we have to consider all of the different barriers to diffusion. So if we're thinking about why is the diffusion of lithium ions so sluggish in V2O5? And so there's an atomistic barrier to diffusion, right? And so as lithium moves through the lattice, so this is some DFT results that Abhishek Parija from our group had pioneered. And so as lithium diffuses through the lattice, it actually goes through a relatively significant change in coordination environment. So it goes from an 8-coordinate site to a relatively constricted 3-coordinate site, and then back to an 8-coordinate site. So there's a lot of bonds between lithium and the harder oxygen lattice that have to be broken and reformed as it diffuses. So this can be quantified through nudge elastic band calculations and kind of examined as a function of what's diffusing through the lattice. But then on top of that too, what we also have to consider is as the lithium ion moves through the lattice, because of the poor electrical conductivity, there's also a barrier to electron diffusion. And in the case of V2O5, where that really comes from is that it has this narrow split off DXY band, and so you can see that here in the density of states. And so this sort of narrow band leads to repulsion of the electrons, so we get splitting into an upper-lower Hubbard band that takes place. And so we don't really get improved electrical conductivity as we pump lithium into this material. And so we've worked a lot in the past at really trying to understand, can we track the extent of lithiation of this material, and we've primarily used the vanadium L edge and the oxygen K edge because, as I'm going to be talking about in a little bit, Stixum played a large part, and so those were edges that we could access in the microscopy. And so we can, we have a really good understanding from the spectroscopy of what happens to the X-ray absorption spectra as we lithiate these materials, and so we know where the DXY orbitals are based on the angle dependence of this peak that we see, and then we also know how these features evolve as a function of lithiation, and so this is going to be critical to some of the things I'm talking about that I'll talk about in a little bit. But then on top of that, I also mentioned that the material undergoes a lot of irreversible structural transitions, and so as we lithiate alpha V2O5, there's sort of this immiscible region between 0.1 and 0.3 lithium. And then we nucleate this epsilon phase and then a delta phase. But then once we go above lithium equals 1 in LAX V2O5, we nucleate this gamma phase, which is a total rearrangement of the structure, and we can't come back from that to access these phases. And what's interesting about this in terms of this material is, unlike a lot of layered cathode materials where the primary change in the crystal structure is just a change in either ordering or in the layer separation, this material actually expands quite a bit and contracts in different directions. So there's a lot of different strain that actually takes place and lattice mismatch between these phases that coexist in materials. And so this presents a problem that I'll talk about a little bit as well in terms of the mesoscale and some of the effects on capacity fade and things like that. And so when you put these things together, you think about the sluggish ionic diffusion and the sluggish polaronic diffusion, the electronic diffusion through these materials. What really is happening in these materials is that there's this self-trapping of a polaron that takes place. So the electron that is given to the V2O5 lattice when lithium intercalates gets localized on a very specific vanadium orbital, the DXY orbital, and it's very stabilized when it's in. So the lithium ion is stabilized within the lattice when it's in close proximity to that polaron, and so really the self-trapping of lithium presents an issue in terms of the coupled polaron ion diffusion. And so, we've been interested in looking at different spectroscopic means of looking at this polaron and the effects of the polaron and tracking this in V2O5 materials, but with an eye towards how do we design these materials, how do we tweak the structure, how do we tweak the composition or the way that these cathodes are formulated to sort of mitigate some of these issues. And so I'm going to be talking a lot about X-ray microscopy, and so I'm sure the majority of the audience is familiar with how this works, but so we have these, typically in our case, they're nanowires, and we can have different orientations of these nanowires, but essentially we're taking 2D images of these, and the images that I'm going to be showing, I think this graphic kind of shows it kind of simply, is that we have, an image, and we actually more or less have a movie, and so at each energy that we scan across, we take an image and we compile these, and so at each pixel we have a spectrum that is contained within that pixel that corresponds spatially to that location, and then we can look at how how these features evolve spatially. And so going back to some of my predecessors' work, so really early on, what we were able to look at is sort of map the different phase regimes within these materials, and so we've got an idea of how these things lithiate, and they tend to show these core shell lithiation patterns, which is pretty consistent with what you'd expect for these kind of layered materials as lithium intercalates from the outside. And if you look at these materials, so basically this is a discharge curve for these. You can see that this is the alpha to epsilon and epsilon to delta, and then delta to gamma. So this is the irreversible phase transition. And so just to give you an idea of how the structure evolves a little more, as you can see here, now we're entering the epsilon phase, and what's happening is very subtly these oxygens are puckering towards the lithium and can sort of coalescing around that lithium and trapping it in place. And so this is kind of what's happening here. And so really the question becomes, how do we address both the sort of the ionic diffusion barrier and the electronic diffusion barrier? And you can see here, this is sort of the localization of the electron on the DXY feature. And before I get into talking about how we've come to address these things and some different methods that we've worked on, really ultimately the problem with this in terms of it goes beyond just the sluggish diffusion kinetics, the electronic and the ionic. But we also, as this lattice mismatch takes place, as these phases evolve, there's actually significant intraparticle inhomogeneity and then also inhomogeneity across particles in these cathodes as these things are cycled. And you can imagine that this creates a lot of intraparticle and interparticle strain that actually creates a problem, can lead to delamination of the materials, fracture of the materials that I'll talk about in a little bit. And so you can see that here. So this is work that was pioneered by David Santos, another member of the group. And so he was able to fib down one of these V2O5 nanowires, and it kind of has a bend in it. And then as a function of cycling, we were actually able to see these things fracture and break as a function of lithiation volume expansion and the strain that takes place. And so in terms of thinking about the battery as a whole, this is really something that we want to mitigate. And so the way that we've sort of leveraged StickSim in a unique way is that what we do is we can process these images through principal component analysis and actually map out the different spectral features that we see. We can assign different extents of lithiation, so essentially compositions to these spectral features that we see to create these higher resolution composition maps. And so what I'm showing now is this is a StickSim image that was converted to a principal component analysis image. This is a statistically processed image. And then we can generate a composition map. And then from there, through some phase field modeling, we can actually get at what the actual local strains are at the boundaries between these different phases. And they can actually, in terms of brittle oxide materials, these strains can actually be very, very high. So this is an issue. So how do we take a material that, it has poor conductivity, electrical conductivity, poor, sluggish diffusion kinetics, and how can we improve it? And so I'm going to be talking about two different approaches. So one is that we can actually look at the mesoscale, and we can start to think about how do we tweak the way the morphology of the material, the shapes of the material to basically improve diffusion kinetics at that scale. And then also, can we go into the crystal structure at the atomistic level and actually change the way that the vanadium and oxygen bonding is so that we can tune the electronic structure, maybe get rid of some of the split off conduction bands that lead to poor electronic conductivity, or alternatively, how can we change the V2O5 structure and bonding to present different coordination environments for ions as they diffuse. And so these are kind of where my work has come in. And so, going back a little bit, we have recently started looking at, so we've sort of statistically within these materials, some of these V2O5 nanowires, the way that they fall within these matrices and these cathodes is that they have these inherent bends or defects in them. And so what we've actually found is that as we look at composition maps within these materials, that curvature within the materials actually, and in turn strain, the way that these materials are strained, actually dramatically affects the way that these things lithiate and the way that the phases orient with respect to each other. And so, typically in a V2O5 nanowire, we see exclusively core shell material, but in these bent nanowires, we see a lot of these interesting sort of striation patterns of localization of these materials. And so we've been able to do a lot of theory and modeling that basically shows that this has everything to do with the way that these materials are curved and bent. And so, this has inspired us to kind of look at, okay, can we use curvature, or the way that these materials are strained to actually to improve the diffusion or change the diffusion and the way that these materials lithiate and the different patterns that form, and in order to essentially mitigate strain that evolves from coarse shell lithiation patterns. And so one material that we've been interested going back for a little bit is on inverse opal structures. And so just to give you an idea of what these are, so the way that we do these is we take a substrate, typically a silicon wafer, but in the case of some of the work that I'm going to be showing you in a bit, we actually did this on silicon nitride STXM grids. And so we essentially make a monolayer of polystyrene beads that these close pack, and we get a nice monolayer of these. And then we subsequently infiltrate this with an organometallic reagent. And then we can basically do a sol-gel reaction to make a V2O5 matrix. And then we calcine this to both crystallize the V2O5 matrix and then also to burn off the polystyrene. And what this leaves us with is this inverse opal pattern. So this is kind of like these things are pretty common in optics applications, slightly less so in energy storage. But what this does is it gives us continuous curvature. And so in the same way that we noticed that curvature in nanowires impacts lithiation patterns, we were curious about how the curvature that's continuous in these materials would do that as well. And so this is some SEM and TEM of these materials. So we're able to, this is on a silicon nitride grid, we can grow these inverse opal patterns, and you can see how these things, they form nice like nano bowls, if you will. And then also what's nice is that in some cases these films are not as nice and they're fractured, and we can actually get IO from these, and so we can actually do our normalization and look at these in transmission mode. And so that allows us to do that. And so, looking at these, what we're able to show is that the curvature that's inherent in these materials, and you can see here I've got a perfectly straight V2O5 nanowire, a bent V2O5 nanowire. So this is a V2O5 nanowire that's strained and curved at this particular point, and then also this inverse opal structure. So these are transmission optical density images. And so the corresponding integrated spectra, averaged across the entire images, are shown below. So the black spectrum corresponds to the straight nanowire, and the red spectrum corresponds to the bent nanowire, and the blue to the inverse opal. And so looking here, what's going on is if you look at the DXY, so essentially, and I should have mentioned this a little bit more detail earlier, what we notice as these things lithiate is that the DXY orbital, which is the split off band at the top of the conduction band, is the first band to populate and lithiate as the electrons are donated to the structure. And so spectroscopically, we see a diminution of that and darkening of that feature as those states are depopulated. The available states are depopulated or are populated by electrons. And so you can see here that contrary to what we expected, so I should mention that these three materials were lithiated under identical conditions. So there's no difference between them. But what we actually notice is that despite the fact that the inverse opal structures are thicker, are larger, it actually lithiates much more quickly under the same conditions than the others. And you can tell that by the darkening of these features here. And that the bent nanowire is kind of intermediate to the two. And so we were curious as to why this is happening. So it seems to be opposite of what we noticed. And so if we dig a little bit deeper and we look at these and we actually do principal component analysis and look at and generate some composition maps, what we see is that around the curvature where this nanowire is strained, we actually get, on the compressive side of the nanowire, we get generation of a hotspot. So something about the way that nanowire is strained there, it lithiates much more quickly on the compressive side of that, and then also is slightly delithiated near the other bend in that nanowire. And then also, if you look at the nanobowls as well, and this is not immediately obvious because the scales are blue to red, but if you actually look at the X in lithium XV2O5 at the bottom, you can see that the degree of inhomogeneity in the straight nanowire and the bent nanowire is actually much larger than in the nanobowls. And so this one ranges from about 0.4, which is firmly in the epsilon lithium V2O5 regime, to about 0.6. Whereas these span, especially the bent nanowire, where this hotspot is extremely lithiated, spans a much wider extent of lithiation and exhibits much more inhomogeneity. And so there's something about this continued curvature that, one conclusion that we can draw from this is that in the case of the bent nanowire, the compressive strain where the material is bent and under compressive strain lithiates much more quickly at that space. So strain can actually be applied to lithiate these much more quickly. But that when we have a single point of strain, the issue is that it leads to much faster rates of lithiation at that point, which can lead to even greater inhomogeneity than in straight nanowires. So one way to mesh both worlds is to create continuous curvature, where we have that compressive strain in terms of the nanobole morphology at all points, but it's continuous so that there's no significant inhomogeneity that arises as a function of rapid lithiation. So one sort of schematic that shows this nicely is that in these straight V2O5 nanowires, we get this sort of typical core shell behavior. But we get core shell behavior in bent nanowires where we get fast lithiation at compressive strain regions, and then we get slow lithiation on the opposite side, but that we get phase homogeneity and rapid lithiation in terms of the continuous curvature. And so in terms of what this looks like in terms of the strain, what we actually see is that not only does it really faster, but because of the decreased inhomogeneity, we also get decreased strain in the nanoboles. And so this is, admittedly not just because of the decrease in the inhomogeneity, but also because the nanobole or the inverse opal structure also has ample space to expand into the boles and sort of mitigate some of that strain that arises during cycling. And this is consistent. So this is some work that was done by a member of our group in collaboration with the Thesis group at Texas A&M University. And so this is consistent with some of these these inverse opal structures that they were able to make in a full cell and look at these. And so we were able to achieve much higher rates in these than in nanowire cathodes. And so this is consistent with what we see in devices. So that's one way that we can kind of look at the mesoscale and start to look at how do we change the properties of these materials in terms of the morphology, the structure, to mitigate some of these sluggish diffusion kinetics. But we can also go back to the drawing board, all the way back to the drawing board, and start to look at how do we mitigate some of these diffusion kinetics from atomistic considerations and electronic structure. So going to take another step back here and start to really think about, something that I did a lot in my work was think about metastability and think about how do we navigate rugged energy landscapes. So how do we actually access metastable materials in space? And so it's really difficult to just set out to design a metastable material. And exploring an entire phase space for these metastable materials is difficult, especially if the only synthetic handles that you have are just pressure and temperature. But despite the difficulty of this issue, it's important to remember that composition is not structural destiny. And so we can start to look at polymorphs of different materials because that gives us different connectivity and can profoundly influence the electronic and the ionic diffusion in solid-state materials for energy storage. So I've been looking at primarily at low temperature topochemistry as a means of accessing different spaces within phase space that are metastable. And so one way that you can think about this is instead of just applying pressure and temperature to change the crystal structure, I'm actually tunneling through phase space through ternary phase space, and that'll make a little bit more sense in a second. So I mentioned before, this is the structure of V2O5. So this is kind of the up, down, down VO5 square pyramid structure of V2O5. And as I showed before, right, we can interpolate lithium, and what that does is pucker the layers and give us different ternary phases. But we hit this at about x = 1, we get lithium V2O5, this gamma phase that has this irreversible phase transformation where we depart this up, down, down structure and go into an up, down structure. So this is a fundamentally different V2O5 sublattice. But what's really interesting about that is I said it's irreversible. And so when we pull the lithium out, we actually stabilize a metastable polymorph of V2O5, different connectivity, same composition. And so what's interesting about this is it allows us to look at how structure and function and electronic structure in particular changes the function of structure and bonding. And so this is just one example of this. And so a lot of work we can also intercalate this with certain organic cations to get different V2O5 sublattices, and then deintercalate those to make different polymorphs as well. We can intercalate this with larger cations to make these one-dimensional tunnel structures, quaternary phases as well. Joseph Handy in the group has been working on this stuff. And then if we deintercalate these larger ions from these structures, we can also get one-dimensional tunnel structures. We can intercalate hydrated ions within the layers of these to get double-layered V2O5 structures, and we can change the coordination sphere on those. And then we can also deintercalate these ions from the double-layered structures to get now van der Waals bonded V2O5 structures that are metastable. We can hydrate this as well, and I'm just going to go through this relatively. I'm going to go through this relatively quickly, but all this to show that we have a very expansive phase space that we've been able to develop, where we've got different materials with the same composition but different structure that allow us to look at energy storage at a very fundamental level. And so I like to joke about this, is what we're doing is playing chemical Jenga. If you've played this long game before, where we can essentially take V2O5 here in the center and put different ions into its structure to mold the V2O5 sublattice the way that we want, and then pull these out to access metastable structures that we couldn't access directly through just application of pressure and temperature. So to highlight a few of these, right, there's a lot of ternary phases that are in here, but just 4 polymorphs that we've been able to work with extensively. So this is alpha V2O5 at the top left. I'm just going to play some of these videos here. It's going to be a little bit noisy maybe, but just so you can kind of see how these things vary. And what this does is it allows us to have a totally different structure and bonding, different diffusion pathways, and also different density of states in terms of the way that the vanadium and oxygen hybridize to give us different states that we access as we lithiate these things. And so, as you would expect, these as lithium, for example, diffuses through these lattices. We've done a lot of theory to look at this. As I mentioned before, that this 8 to 3 to 8 change in coordination environment that lithium undergoes as it diffuses through alpha V2O5 is very stark and sort of precipitous in the way that it drops off, and this presents a large ionic diffusion barrier. But as we go into gamma V2O5 and zeta V2O5, these changes in coordination environment change in 2 ways. One, there's fewer bonds that break and form as the lithium ions diffuse, and that gives us smaller diffusion barriers. You can see here much lower for zeta V2O5 in particular in this third one. But then also the transition states that they go through are actually a little bit larger in terms of they're not as constricted, and so that also helps us a bit. So I'm going to be talking primarily about zeta V2O5. And the way that zeta V2O5, by rearranging the V2O5 framework, has allowed us to actually not just intercalate lithium much better than an alpha V2O5, but also achieve magnesium ion intercalation. And so I mentioned that a lot of the electrochemistry that I'm going to be showing here was done in collaboration with Jordi Cabana's group. Did some really beautiful electrochemistry here in one of the first materials, oxide materials that was shown to have magnesium intercalation. So the first thing, and this was done in collaboration with Alex Moses' group at University of Saskatchewan. So what we were able to show is that as we change the structure from a 2-dimensional structure, an alpha V2O5, to a 1-dimensional structure, one interesting change here is that there's a more crystallographically unique vanadium sites, and what that does is gives rise to a more dispersed, essentially density of states within the conduction band. And so the vanadium split off DXY state that you see here in the alpha V2O5 is not present in zeta V2O5. And so by having a larger number of vanadium states that are these states that are accessible, it basically essentially reflects the increased covalency of the structure. And so that was one thing that we were excited about to look at. And so just to take a step back, so this should have come first, but for those more interested in the synthetic aspect of this, the way that we do this is we intercalate, for example, silver or copper into the structure of V2O5 to rearrange it, and then we can etch this out with acid to form these one-dimensional structures. This is a nice close-up view of that. And so what we initially did was just do topochemistry. So we were able to reversibly intercalate magnesium into the structure and then pull it back out to show that magnesium actually is going into the structure. So this is actually a very difficult thing to do. I should have mentioned that before, but lithium ion diffusion is much easier because it's a monovalent ion. There's only one polaron, one electron that's moving with the lithium through the lattice. But in the case of magnesium, you have a divalent ion and also two bipolar on that forms in these very insulating materials. So we were able to show through some X-ray diffraction, solve these structures, and basically show that we do actually get magnesium in here, and it sits exactly where we expect, and we can actually image these magnesium through EDX within these tunnels. And so this was very exciting work that we were able to do, and really and we were able to show that we can reversibly intercalate magnesium here very well at the time. But the important thing to take away here is that what we did is essentially by tunneling through metastable phase space, we were able to create vanadium oxides with different structures. And that different structure that we see has two impacts. Is it changed the coordination environment, which is less harsh of a change than in alpha V2O5, but then also we got to obviously get a different electronic structure, which reflects a greater degree of covalency, which helps to improve the electronic diffusion as well in this material. And that what emerges from that is that not only are we able to intercalate lithium much better, but we also avoid some of these phase transformations that we see in alpha V2O5, but then we're also actually to cycle magnesium reversibly. And then going beyond that, recent work that was primarily done by Joseph Handy, as we're actually able to make single crystals of these metastable materials as well. So this is single crystals of zeta V2O5. They're nice and yellow, just like alpha V2O5. And what we can do is then actually topochemically lithiate these things and actually look at where the lithium in single crystal X-ray diffraction, where the lithium sits within these materials, and actually image these diffusion pathways. And what's really cool about this is that it not only accurately confirms a lot of our nudge elastic band calculations that we've done in terms of where the lithium goes and how it diffuses, but we've actually now been able to get up to 3 lithium into zeta V2O5, whereas without significant phase rearrangement, because it's a one-dimensional tunnel structure, whereas as I mentioned before, in alpha V2O5, these phase transformations prevent us from getting beyond 1 lithium per V2O5. And through STIXM, we've been able to show that really that the phase homogeneity in these materials, because it's a one-dimensional tunnel structure, is much greater than in alpha V2O5, where we get these core shell patterns. Really, in zeta V2O5, we're not able to detect significant inhomogeneity in terms of the way that these lithiate. And then there's also some interesting X-ray emission work that we're doing on this as well. We're able to see basically multiple DXY features that derive not just from the population of the DXY features, but also some of the other states that get populated as we go beyond, reducing beyond vanadium 4+. So just to summarize a bit, really what this work does is, so we've looked at sort of this canonical V2O5 system that's really a good model system, in part because it's not great at what it does, and looked at different ways that we can tune the mesoscale properties of the material, as well as atomistically to improve diffusion kinetics, to mitigate some of these strain issues that we see at the device level. And with that, I would like to thank you for your attention and for the opportunity, and I would be happy to answer any questions.